Hello everyone. In our today's video, we will be discussing the P block elements and specifically group 15 elements. As we know, group 15 element comprises of 5 elements which are nitrogen, phosphorus, arsenic, antimony and bismuth. This particular family is also known as nicogens, or sometimes we call it nitrogen family since nitrogen is the first member of this group. So let us try to see in detail that how this group shows the trends in physical and chemical properties, what are the different oxidation state it shows, how to write the electronic configuration. So all these topics we'll be trying to cover in our today's video. So going for the introduction of the group 15 elements, nitrogen is the first member of group 15. That is what we call as 5A, okay, of the periodic table. It consists of 5 elements as we have discussed, that is nitrogen, phosphorus, arsenic, antimony and bismuth. The elements of this group are collectively called nicogens, remember that. And nitrogen and phosphorus of this particular group are non-metals. Antimony and bismuth is metalloid, and the antimony and arsenic is metalloid and bismuth is a metal. Now the question is, why there is a change in this particular character? As we go down the group, the metallic character increases. Always remember that in any group, irrespective whether it is S, P or D block, whenever we move down the group, the metallic character increases. Now, why metallic character increases? It's because whenever we move down the group, ionization enthalpy decreases. When ionization enthalpy decreases, the tendency to lose electron or the electropositive character increases. With the increase in electropositive character, the metallic character also increases. That's why bismuth tends to become pure metal in a group where nitrogen and phosphorus on the top of the group are behaving as pure non-metal. And in between, we have other two elements which are behaving as metalloids. So as we move down the group, slowly the metallic character increases. It is because of the low ionization enthalpy or the decrease in the ionization enthalpy as we move towards the heavier element. Okay. Now coming for the next, that is the electronic configuration of the group 15 elements. Okay. As you can see on the screen, the 5 elements, okay, if we write the electronic configuration, if I start with nitrogen, atomic number 7, it will be 1s2, 2s2, 2p3. So instead of writing 1s2, I can write He, which is nothing but the configuration of helium. So we can write in this brief way, instead of writing 1s2, 2s2, 2p3. So 1s2 actually stands for, or helium stands for 1s2. In similar way, phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. So 1s2, 2s2, 2p6, which is a configuration of neon. So I can write Ne instead of 1s2, 2s2, 2p6. So in this way, if you go for arsenic, you can clearly see on the screen, it's argon 3d10, 4s2, 4p3. If I go for antimony, if it is krypton, 4d10, 5s2, 5p3. If I go with bismuth, it is xenon 4f14, 5d10, 6s2, 6p3. Okay. And if you see their atomic number, the atomic number of nitrogen, if you see it's 7, then it's 15, 33, 51, 83. How to remember this? It's very simple. If you come from 7 to 15, it's addition of 8. 15 to 33, it's addition of 18. 33 to 51, it's addition of 18. 51 to 83, it's addition of 18. So what basically you do is you add 8 first, then 18, then 18, then 32. This is applicable in P block elements. If you start from the second period, you can do it in any group. So when you start from the second period of the periodic table, if you add 8, the next atomic number you will get. Then if you add 18, you'll get next. If you add 18, then you'll get the next. And lastly, if you add 32, you'll get the last one. So that is how we can get the atomic number instead of by hearting it. We need not by heart it if we just remember the first one, and remember that if it's starting from the second period, I just need to add 8, 8, 18, 8, 18, 18 and 32. That is how actually we can remember the atomic number. Okay. So Coming for the configuration, if you see the configuration, the similarity in the configuration, there is 2s to 2p3, 3s to 3p3, 4s to 4p3, 5s to 5p3, 6s to 6p3. So if you see this configuration, the outer shell configuration in all the elements of this group is same. So as a result of which, the general outer electronic configuration can be written as ns2np3, where n stands for the principal quantum number of the last shell, okay, which varies from one element to the another. So it varies from 2 to 6. Coming for the next, which is oxidation state. Now this group shows two types of oxidation state, which we call as positive and negative oxidation state. The positive oxidation state, which this group shows, is +3 and +5, which is very clear from its configuration. Its configuration is ns2np3. So if it loses all the electron from s as well as p, the total of 5 valence electron, which is the maximum oxidation state which it can show, that will be +5. That is the group oxidation state. Other than that, it can show +3 oxidation state also, where it loses only the p3, not the s2. Okay. Now, it was found out that as we move down the group, the tendency to lose this 3 electron increases. That means the tendency to show +3 oxidation will be more than the +5. This particular, the reason for this particular trend in the oxidation state is due to inert pair effect. Now, what is inert pair effect? That is what we'll be trying to see next. But before that, let us just see the negative oxidation state. What is negative oxidation state? Basically, it's the tendency to gain electron. Now, if you see the configuration, it is ns2np3. That means if it takes 3 more electron, it will become p6. If it will become p6, it will become noble gas configuration, which will be the nearest noble gas of the respective elements. As a result of which, this element will prefer to take 3 electrons. But the tendency to take this 3 electron, or the tendency to show -3 oxidation state, decreases down the group. Why? Obviously, the elements, when we move down the group, their size will increase. With increase in size, their electron gain enthalpy will decrease. Their electronegativity will decrease. As a result, they will not be able to gain electron. As a result, the tendency to show this -3 oxidation state will become less as you move down the group. So the first few elements like nitrogen and phosphorus will be able to show this -3 oxidation state, particularly nitrogen. The other will not be able to show. Okay. So if I try to sum it up, then the most common oxidation state which this particular group will show is +5, +3, or -3. These are the 3 most common. Remember that. Other than this also, they show the other oxidation state, but this will be the most common oxidation state which this group will be showing. Now, coming for our inert pair effect. Now, what is this inert pair effect? Remember that this effect is nothing but it is the reluctant of the s electron, which we can see in the configuration ns2np3. That s2, that pair of electron, is reluctant to take part in bond formation for the heavier electron. Now the question is why? The reason why they are giving is it is nothing but due to post shielding effect or screening effect. Now, what is this screening and shielding effect? Most of the students get confused in this particular topic. Remember that, keep it very simple. Whenever we take a particular atom, an atom will have attractive force and will have repulsive force also. Attractive force is between the nucleus and the electrons, and the repulsive force is between the inner electron and the outer electron. As a result of which, the outer electron will not get the full nuclear charge from the nucleus because it will be getting repelled by the inner electrons. So as a result, the attractive force which the outer electron will experience will be less as compared to the inner electron. So as a result of which, it feels like that the outer electron is screened from the nuclear charge by the inner electron. That's why we call it screening effect or shielding effect. Basically, it's the repulsive effect of the inner electron towards the outer electron. Now, this particular effect depends, or when the repulsive effect will be more or less. This particular effect depends on where the inner electron is present, in which subshell it is present, in which orbital it is present. It was found out that if it is present in S or P, then this repulsive effect or screening effect is more. That means the outer electron will get repelled more. But the same thing when the repulsive effect, actually, if you take it for D and F electron, it was found out that the repulsive effect or shielding effect is very poor. That means if the electron is present, if the inner electron is present in D and F, the repulsive effect which they will show towards the outer electron will be very less. Now, why? It is because of the size of the D and F orbital. They are very big, scattered, diffused in space. As a result, the repulsive effect which the outer electron will get will be very less. And because of which now the nuclear charge which the outer electron will get will be very high. Now, because of that, just try to see the configuration which you can see in the screen. If you see the nitrogen and phosphorus, which is the second period and the third period element, there is no D electron or F electron in this particular period. So remember that whenever we call inert pair effect, it is actually, this effect happens after the fourth period. Okay, or starting from the fourth period, fourth, fifth, and the sixth. Why fourth, fifth, and the sixth? Because in this fourth, fifth, and the sixth period element of the P block, inert pair effect is a phenomenon which is happening in P block. Okay, and in this fourth, fifth, and the sixth period elements of the P block, the inner shell contains electron in D and F. And once the inner electron will have electron in D and F, what will happen is, you can clearly see in the screen, like arsenic has 3d10, antimony has 4d10, and bismuth has 4f14 and 5d10. As a result of which, what will happen is the repulsive effect towards the outer electron, that is in case of arsenic it is 4s2 4p3, in case of antimony it is 5s2 5p3, in case of bismuth it is 6s2 6p3, will be very less. Because of which the attractive force which this s electron which will experience will be very high. As a result, this s electron will not be so easy to unpair and make it actually take part in bonding. As a result, it will be reluctant to take part in bonding because of high nuclear charge which this will be experiencing because of the poor shielding effect of D and F electron. Because of which, what will happen is only the P electron in this particular system will prefer to take part in bonding. So as a result, the preference of oxidation state which this particular elements will try to show is +3 instead of +5. So +3 will be more preferred if you compare with +5. Why? Because of inert pair effect. Inert, it will not be reluctant. It will be actually, what do you call it? It will be not taking part in bonding. So that's why we call it inert. Pair, it is two pairs of s electron and effect. That's why inert pair effect. Okay. Now, coming for the next topic, anomalous property of nitrogen. So whenever we talk about anomalous property, always remember that it's not only for nitrogen, but any element of, or any element which is first in the group. Okay, in any group, whether it is S block or P block, which is first in the group, will always tend to show some properties which is different from the rest. Okay, whether it is S block or whether it is P block. Now the question is why? Remember that this basic, or the basic reason why the elements of the first group will be, or the elements of the first element of any group will prefer to show actually different properties than the rest, is because of its small size. Obviously, it is the first element, so it will have very, very small size. It will have high electronegativity. Obviously, because of small size, the electronegativity will be very high. High ionization enthalpy, again related to size. When size is small, high ionization enthalpy. And lastly, since this first element of any group belongs to second period of the periodic table, and the second period does not have D subshell. Remember that. Okay, second period element will not have, since they'll have only two shells, principal quantum number will be 2. For principal quantum number 2, you have S subshell and P subshell, not D subshell. So there will be no vacant D orbital in this system. And because of these 4 reasons, they tend to show some properties which will be completely different from the group, which is not expected, because when we say a group behaves similarly. That's why they are called a group. Okay, because their electronic configuration is same. Their oxidation state tends to actually remain same, because of which they tend to show similar chemical and physical property. But this particular element of any group, okay, the first element will tend to show different physical and chemical property than the rest. Some of the physical and chemical property will be different. And particularly here, since we are talking about nitrogen, so nitrogen tend to show some different physical and chemical property. So what are those physical and chemical properties? So let us try to take few and understand it. So the first one is nitrogen is diatomic, unlike other elements of the group. Remember that nitrogen exists as N2. The other element do not exist as N2. Phosphorus exists as P4. Okay. So why nitrogen is the only element which exists as N2? It's because of its small size. Try to understand the configuration is NS2 NP3 for this particular group. Or for nitrogen, it is 1s2, 2s2, 2p3. P3 means there will be one electron in 3p orbital, 3 unpaired electron. So one unpaired electron will try to form a bond with another nitrogen. So one unpaired electron of one nitrogen, another unpaired of one nitrogen will overlap, will form a bond. And since the size of the nitrogen is small, the overlapping will be very actually close, and the atom can come close to one another, can come very close to one another. After that, what will happen is the other pair, okay, other p orbital which are present can laterally overlap and form pi bonds. So there are two other p orbital which are left, so they can form a lateral overlapping and can form pi bond. So the first one will form sigma bond, the other two will form pi bond. As a result of which they can form nitrogen-nitrogen triple bond and will exist as diatomic molecule. But the same thing, why not the rest of the element? They also have the similar configuration. The rest of the element are big in size. So even if they come close and form the first single bond, remember that since their size is big, when the rest of the p orbital, which the unpaired p electron will try to overlap, it will not be able to, because of the size of this particular element which are big. So there will be no effective overlapping, so it cannot form multiple bonds. So this multiple bonds which this particular system forms, we call it p-pi multiple bond. The p orbital in two systems are involved in formation of pi bond. As a result, multiple bonds exist in this system, and it happens for nitrogen. So nitrogen can form p-pi multiple bond. That's why it is diatomic. Rest cannot form. Why? Because of its bigger size. That is one. The another one is nitrogen is the only element which exists as gas. The rest will not exist. Why? Now, since nitrogen exists as N2, this 2N2 molecule will be held to one another by weak van der Waals forces. And these weak van der Waals forces can be easily overcome by collision of molecules at room temperature. When you bring these molecules to room temperature, they will easily collide and break their intermolecular force and hence exist freely as gas. Where if you talk about the rest of the element, their van der Waals force will be strong and make them exist as solid. Like P4 or phosphorus is a solid. Okay. Coming for the third, nitrogen does not show pentacovalency. Nitrogen cannot form 5 bonds, but rest of the element can form 5 bonds. Now, why it is? Just to make you understand that, you can see the configuration of nitrogen. It is 1s2, 2s2, 2p3. You can see clearly p orbitals have 3 unpaired electrons, which we are talking about. Now, try to understand, after 2p comes 3s. There is no 2d, I have told you. In second shell, you don't have any d subshell. As a result of which, the electron in 2s cannot excite to the 3s. That type of excitation is not possible from the second shell to the third shell. As a result, only this 3 can take part in bonding, which makes it covalency 3. Or maximum, this unpaired electron can be used to form a coordinate covalent bond, which it forms in NH4 plus ammonium ion. As a result, it can form 4 bondings. So nitrogen can show a maximum of 4 bonds. But phosphorus, if you see, the phosphorus on the other hand will have 3s2, 3p3. So the 3s electron can easily go to 3d orbital, which is vacant. And in the same subshell, third shell has d orbital. As a result, the electron from 3s can easily be promoted to 3d, and it will go in excited state where it will be having 5 unpaired electrons. So it can form 5 bonds. As a result, phosphorus and rest of the other element can show a covalency of 5, whereas nitrogen will not be able to. Why? Because of the absence of d orbital in its valence shell. Why it does not have d orbital? Because it is an element of the second period. Okay. Coming for the trends in chemical reactivity. So we'll be trying to take few chemical reactivity, how it reacts, okay, as a group. So first, reactivity towards hydrogen. Remember that any element, whether it is metal or non-metal, when it forms bond with hydrogen, binary compound with hydrogen, we call it hydrides. So basically they form hydrides. Okay. Remember that all the members of this group, okay, starting from nitrogen to this much, generally will form hydrides of the type EH3. Like nitrogen will form NH3, phosphorus will form PH3, arsenic will form ASH3. Okay. All hydrides will be pyramidal in shape. So all the hydrides will be having pyramidal shape. Okay. Whenever you talk about their basic strength, the order which they follow will be this. Ammonia will be the most basic, then phosphine, then ASH3, then SBH3, then BIH3. Now, why ammonia is the most basic? Why it has the highest basic strength? It is because of the size of ammonia. And remember that what kind of base are they? They are Lewis base, because all of this will are having 3 electrons. So the s electron pair which they have will remain unpaired, and that lone pair can be donated to other system, and a system which can donate a pair of electron is nothing but a Lewis base. Okay, so all of them will have unpaired electron, lone pair, which makes them behave as Lewis base. Now try to understand that, because since they act as Lewis base, now the question is which has the highest basic strength? It's ammonia. Why ammonia? It's because of its small size. Because of its small size, the charge density which it will have will be very, very high compared to the rest, because as the size increases, the charge density, the lone pair, the density on that particular atom will be less. As a result, the tendency to donate electron will also become less and less and less. So ammonium or ammonia will be the most basic in this case. Coming for the next, NH3 is thermally most stable. Now, if you compare this particular element, the thermal stability, which we say, okay, which can resist more heat, remember that ammonia is the most stable. Means if I take all these 5 hydrides and heat them, ammonia will be most stable and bismuth will be the least stable. Now the question is, why bismuth is least stable? Remember that the least stability of bismuth is because of the bond distance of this particular bismuth and hydrogen bond. And if you compare the bond distance of nitrogen and hydrogen bond, when you take nitrogen and hydrogen bond, nitrogen is very small, as a result of which the nitrogen and hydrogen bond will be shorter, and shorter bond will not break easily when you heat it. But the same thing when you take bismuth and hydrogen bond, bismuth is very big, as a result of which the bismuth hydrogen bond will be very long, as a result of which it will be breaking very easily. So at temperature, when you increase the temperature, the thermal stability or the stability of BiH3 will be very less. It will be decomposing very easily. But the same thing, NH3 will not be decomposing because of its shorter bond. When we talk about the reducing character, it's the same concept. Remember that when the bond will break easier, okay, in BiH3, what will happen? Hydrogen will be given very easily. When the bond will not break in ammonia very easily, hydrogen will not be given easily. As a result, when a system can give hydrogen easily, it will act as a better reducing agent than the other system. So as a result, now bismuth will be, or bismuth hydride will be a very good reducing agent compared to ammonia. So it is just the opposite case. The concept is same. Okay, it is because of the bond length, but since the bond length is shorter, it will not break. If it will not break, it will not give hydrogen. As a result, it will not act as a reducing agent. So very important discussion on a very important topic in the reactivity of hydrides, okay, of group 15. Coming for the next, reactivity towards halogen or formation of halides. Okay, the members of the family of this particular family forms 2 kinds of halides. If they react with halogen, either they form EX3, E stands for the family, and X stands for the particular halide, or EX5, like phosphorus form PCl3, PCl5. The trihalides, if it forms EX3, okay, then it will be sp3 hybridized and it will be pyramidal in shape. Remember that. And when it is pentahalide, the hybridization will be dsp3d, and its shape will be trigonal bipyramid. Please remember that it is general for all. Okay. And remember that nitrogen will not form pentahalide, as we have discussed, because it does not have any d subshell or d orbital in its valence shell. All the others will have, as a result, all the others can form pentahalides except nitrogen. And remember that pentahalides will be more covalent in character than trihalides. So if you take the covalent character, then pentahalides will be more covalent than the trihalides. Now, what is the reason? Remember that it is because of more polarizing power of the pentavalent cation in case of pentahalides, and because of which it's because of the more polarizing power of the cation, because of its smaller size and high charge density, it tends to have more covalent character than the trihalides, which we discuss in Fajan's rule, which we give in the form of Fajan's rule, right? So according to this Fajan's rule, whenever a particular element will have high charge and small size, whenever a cation, you can say not an element, but a cation will have high charge and small charge, high charge and small size, such elements tend to show more covalent character than the rest of the cations if you compare the covalent character in such molecules. So remember that if you compare pentavalent and pentavalent halides and trihalides, in pentavalent halides or pentahalides, you have pentavalent cation. In trihalides, you have trivalent cation. So pentavalent cation will be smaller in size and will have high charge, because of which it will have more polarizing power. Because of more polarizing power, it will be having more covalent character. So remember that. Coming for the reactivity towards the oxygen. Okay, so this particular oxides, the oxide which it forms is E2O3 and E2O5. Okay, these are the two types of oxide which it forms. Okay, the oxide in the higher oxidation state is more acidic than the oxide in the lower oxidation state. That means E2O5 will be more acidic than E2O3. And the acidic character, remember that if you compare of any oxide, whether E2O3 of any group, of this particular group, or E2O5, then as you go down the group, then the acidic character will decrease. So these are the general trends in chemical and physical properties of group 15 elements. Okay, so that is how we can understand the general trends in physical and chemical properties of the members of the group 15 elements. So thank you, everyone. Do subscribe for this channel for explanation on various topics in chemistry.